So it's another satellite-based topic this month. But I thought rather than give you a history of our last 5 generations of onboard processing of satellites, I would talk about something new. So I'm going to talk about our latest, which is our 5th generation, which is our OneSat satellite. So as a consequence of a bit brag a little bit, I'll tell you all the technical details, and I have to be a little bit cautious in answering some of your questions. But I hope to give you a flavour of the type of technology that we're able to fly these days. So I've called it supercomputing power in space. Why have I done that? Well, let's start with the state of the art in terrestrial superconductors. So modern supercomputers are used for data, artificial intelligence, things like climate modeling, like that. And they're doing a rate in the exaflop range. And the biggest all kinds of figures, but the one I picked out of the news reports was 216 petaflops, or 0.2 exaflops. So you've got mega, giga, tera, peta, exa. So it's up there, and that is built using a big rack system. So you can see bottom right the news picture from BBC July last year, 14th station. And you see a model basically got a NVIDIA, what they call a super chip. It's effectively it's a package with a lot of silicon all packaged together without using a printed circuit board. He's holding in his hand something. It's got a very large graphics processor and a large CPU, and then essentially that goes into a rack, which he's standing next to, part of, and you put 5,000 or so of those together, and you get a supercomputer. So this is a bit of a beast. It takes 5 megawatts of power, so you almost need your own power station, and that power also gets turned into heat. So the blue and red hoses that you can see there are actually the water cooling system. Obviously, cold water in comes out warm, and they intend to use that to heat some local houses when they've installed that. So that's the kind of scale we're talking about for a modern supercomputer. It's also quite heavy at 150 tons, so this is not what we're going to be flying on a satellite that we're going to launch into space. But what we are doing basically is using very similar level of technology, but a smaller number of modules to support our onboard computing telecommunications satellites. So I'm going to talk about telecommunications satellites operating in geostationary orbit, and explain why they need such high computing power, what it's doing, and a little bit about how we do it. In particular, the technologies used are similar. This supercomputer has a custom integrated circuit, a chip, basically a large chip built by NVIDIA specifically for this kind of purpose. We have our own integrated circuit that we built specifically for our purpose. We put these together in a network to build a large processor. And it's interconnected via optical fibers, high-speed digital optical connections, connected all together into an interacting network. We have to have an advanced cooling system. That's a bit more difficult in space than on the ground. And the cheat that we take for telecommunications processors is that our processing is application specific. So we're not really talking about a general purpose computer. It's totally reprogrammable. We are doing certain telecommunications functions which are highly configurable, but it can only do telecommunications functions. It can't, do your bank account or anything else like that. So that's where we pull back a little bit compared to the state of the art technology. On the other hand, we have to make sure that our technology works in a space environment, quite a harsh space environment, and it has to operate continuously for typically 15 years, continuously routing telecommunication signals from users on the ground. So why do we require superconducting capabilities? Well, I'll start with a simple animation of a geostationary satellite. It's going in circular orbit over the equator, in this case over the Americas, and it has a orbital period of 24 hours, so it exactly matches the rotation of the Earth, and therefore it appears to be stationary from any point on the ground underneath it. So, for example, this might historically have been used for a TV satellite, maybe broadcasting TV to the whole of South America, for example. That's exactly the sort of history how telecommunications satellites started. But today that isn't very interesting. We're not in an era of broadcast, we're in an area of Netflix on demand. So what we need today is point-to-point communications. So rather than effectively illuminate a continent and broadcast TV, what we have is a much more complicated antenna system, which can give us hundreds of beams, spot beams, very narrow beams pointing over a region of the Earth, and communications in each of those beams independently. And that's very important for satellite communications because we only have a very limited bandwidth, limited spectrum that we can use. The biggest spectrum that we have for satellite communications is 3 gigahertz, which, if you imagine, is about 3,000 megabits per second. It's not many home routers worth. So we can't actually finance a satellite to do a tiny amount of traffic like that. We have 100 beams or more, each using the same bandwidth over and over again, using a complicated antenna to actually separate the traffic out spatially to different areas. A beam might be a country, or a part of a country, for example, has its own traffic. So in order to do that, you need a large antenna, and antennas that can generate hundreds of beams are typically not fixed antennas, they're active antennas. They're formed they're not just like a satellite dish, they have many antenna elements, each independently transmitting, and you can effectively electronically steer beams and form multiple beams wherever you want by controlling the amplitude and phase on the signals for all of these elements. So you may have 100 element antenna, and to control the signals to all of these, whether you're transmitting or whether you're interpreting the received signals, you need a large digital processor to process the signals from all of those feeds, separate out the beams, separate out the traffic channels, and basically isolate the individual users, the individual traffic channels that are being transmitted. So I have a model of part of the antenna behind me. So you can see that poking out of the satellite of order 100 feeds. I'll move on to this a little bit more detail on the next slide. Behind that, we have a digital processor, which is processing the signals from all of those feeds. So we have typically 100 feeds. We have typically several gigahertz of spectrum, so maybe we have to sample at several times several gigahertz, so maybe 10 giga samples per second on each feed. You multiply 10 giga samples per second by 100 feeds, you get a whatever the next one is, a tera sample per second. And then if you have to do 100 operations on each of those things to do the processing we need to do, you end up with 0.1 petaflops. So it's about 1,000th the capability of that Isambard computer that I showed you in terms of actual operations that it's doing. That's what we need basically just to process the signal from that antenna. That's the primary reason that we're doing it. So just to give you an idea of the reason behind those numbers, at the bottom right, I've got a little diagram of the satellite in geostationary orbit around the Earth. So we're at a height of 36,000 kilometers for the 24-hour period. The diameter of the Earth is just over 6,000 kilometers. If you do the trigonometry, you find that the Earth subtends 17 degrees angle from geostationary orbit. So if you remember that figure, and I move on to the next slide, what I've got on the right is a picture of the Earth, and I've drawn a little grid, 17 squares by 17, so they're effectively 1 degree graticule. And then I have on the left a spot beam pattern, something that we might want our antenna to generate. I will move it over the Earth shortly, but what I've got is 100 spot beams. So this is not the same as the 100 feeds I've got. Each of those spot beams, one spot beam is formed by a combination of the signal from all of those 100 feeds. But we have a similar number of beams to feeds typically. And I've drawn them in different colors, red, blue, and green. So you can imagine, for example, that our 3 gigahertz of bandwidth that we've got is split into red, green, and blue colors, 1 gigahertz of each for each color. And we just fill the Earth, the space that we want to cover with signals in the 3 different colors. The point being that we've got roughly circular beams. If we don't want any gaps between those circles, we have to overlap them a bit. And where we overlap, we can't use the same frequency in adjacent beams. So we use maybe 3 colors in a regular sort of hexagonal pattern like I've drawn that. And then if you had 100 beams, 3 gigahertz of bandwidth, and only 1/3 of it usable in any one beam, you end up with 100 gigahertz capacity. So that's basically 100 gigahertz of capacity is the capacity of our satellites, and that's what we're intending to do. So just to show how that might be useful, I just move that across and say, imagine you have a satellite operator who wants to do Brazil and its environs. Those beams are 1/2 a degree wide. So I've drawn them exactly half of a graticule, and I've put them over Brazil and the surrounding regions, and you see that that makes a scenario for a customer to use as this. So again, that's sort of something behind the scale of the processor. So really, this is about the antenna. I wanted to say a little bit about the antenna because the antenna is designed in Stevenage. So we're here really because the processor is designed in Stevenage, but the antenna is also designed in Stevenage. It's a very complicated subsystem. I have a 3D printed metal model here, which is a little bit heavy, but I'll tilt it towards you. This is the model of a receive antenna, roughly 100 feet. It's a little bit fewer than that. Exact numbers I'm not going to share. And what you can see is the bit that points out of the spacecraft. So those are the horns that face towards the Earth, or in some cases they face towards a reflector which illuminates the Earth. And in this case, it's for a Ka-band system, so 30 gigahertz frequency band, which is the one where we have most of the capacity, which means the wavelength of the light, the microwaves, is about 1 centimeter. So you can see the sort of feed size is about this, a little bit bigger than the wavelength of the light. So the top feed part of that, the top few inches, stick out of the spacecraft, the rest sits behind, and then behind all of this, I'm going to pop it down because it's heavy. The antenna subsystem includes filtering, but it also includes all the amplifiers. So on the receive side, we have low noise amplifiers that pick up the very faint signal transmitted from users on the Earth. And on the transmit side, we have high power amplifiers that generate the high power signals that get the signal back to Earth for the receivers on the ground. All of that's part of the antenna subsystem. It generates a lot of heat, all those amplifiers. So there's a hugely complicated mechanical and thermal system to get heat out of that structure. Unfortunately, I can't show it to you because it's new. So I just have a little look that says it's an interesting subsystem. The interesting thing is it's all designed here in Stevenage. So we're very proud of it here. So now I'm going to move on to the short, it's a marketing presentation, but a short video of the satellite that all this goes on. So the satellite Airbus is currently developing, it's called OneSat, and it's a generic design of satellite that's intended for multiple customers. So all of this new technology is very expensive. Historically, every time we've had a new customer, we have designed a bespoke satellite for the particular customer. Here, the idea is that we have multiple customers. They all buy the same satellite, but we can reprogram it to do the coverage area, the size of the beams, all that kind of thing that they want by virtue of having this active antenna and a digital processor that's reconfigurable behind it. So there's an awful lot in about 90 seconds. So I will pause and see if there are any questions on it afterwards, but it shows you the satellite as a whole. It shows you the kind of orbit that it's intended for. And it also shows you some example use cases showing some slightly more realistic beams than what I showed you, which was a toy model that I did with circles in PowerPoint of how you might really use this. So if we're ready, I will just move on to the presentation and let you watch. So I don't know if anyone wants to ask any questions on what they've seen so far. Yeah.
I've got one very quick question, on one which will probably be a little more involved. On the thing with fires, looking at all the power dissipations and the peta and exaflops, Islam is holding a little unit. Doing some very quick mental arithmetic while I was watching that, does that really dissipate 1 kilowatt?
Yes, that's a good question. I mean, it will be, I mean, that is possible. I'll show you an example of a single chip dissipating a kilowatt next.
Because, I mean, presumably that's related to the number of flops per second.
Yeah.
So, I mean, to me, a lot of electronics stuff, that just seems fantastic.
I think it will dissipate of that order, yes. That's why it's got the water cooling.
And the other thing is, I think in the second or third slide, there was 100 gigahertz figure. So can you explain what? I think I'm getting a little bit confused between bandwidth and baud rate.
So gigahertz is the actual useful capacity of the satellite.
So what is that?
So it means that if I summed up all of the traffic that was going through the satellite and how much bandwidth it needed, how much spectrum it used in transmitting, it would add up to 100 gigahertz. So there isn't 100 gigahertz of spectrum. We're saying we're using 1 gigahertz in this beam, or 1 gigahertz in that beam, 1 gigahertz in another beam, and there could be 100 beams with 100 gigahertz.
Right. So each occupying the discrete bit of the electromagnetic spectrum. Why is that an interesting question?
Because it's large. Conventional satellites only have 1 or 2 beams, well, a handful of beams, 10 beams or something like that, and the bandwidth is still the same, so they can only do a fraction of the amount. So this big antenna and this it's a very good question. I didn't make that very clear. This antenna and the processor that sits behind it are effectively the means that enable us to do more than 10 gigahertz of bandwidth. We're talking 100 gigahertz now, for example.
I see what you mean now. Basically, it's just a way of saying how many signals you can have in order to test this.
Yeah. Yeah, it's basically the capacity of the satellites.
Brilliant. Thanks.
All of this one will be doing all of the receive. There'll be another one doing all the transmit for users. But you saw some large dishes on the
those will be steerable dishes aimed at gateways. So you'll have a big station on the ground with a 20-meter dish or something, which is where all of the traffic is accumulated for, the operator of the satellite, for example. So there will be a small number of those, which you can count basically from the number of dishes on the satellite. And they will be communicating with users all over the coverage region, all over South America or Malaysia or wherever it is. With the 100 individual beam over. So the gateways have a little bit more bandwidth, and actually they have to be scattered around the world because they can't take 100 gigahertz. There's not that much spectrum, so you still have to have multiple gateways. Those are effectively the big dishes that you see on the satellite. So no, it doesn't do all of them, but it will do all of the receive. It will do, let's say, all of the receiving side from users, and then what came in on that antenna will be transmitted via the dishes to a small number of gateways, and then there'll be stuff going in the other direction because all this communication is two-directional, and you will effectively have some dishes receiving and transmitting through another antenna like that. So it's a
simultaneously. No, this is simultaneously doing all of them.
If this were 100 feeds, which is the right sort of magnitude, we would have 100 different signals. Well, if this was transmit, it's easier to understand. We would put 100 different signals in there. That would be all of the beams and all the traffic combined. We would have used the digital processor to play with the amplitude and phase of all the different signals. And then when that hit the Earth, there's a sort of interference pattern from all of those separate signals. It would form that beam pattern with all the right signals in the right places. That's the idea. And the receive direction is just the sort of mirror image of that.
Is it one satellite per customer? It's a bespoke. So mostly
more than one, so it depends on the customer. The idea really it's a medium-sized satellite. So if you're a regional operator, if you're a country, then you buy one, and it would do all of the communications you wanted in your country and your neighbors that you talk to. If you're a global operator, you might want several to give you, fill in gaps in your coverage with your big fleet of satellites you've already got, or to replace some of the existing ones.
the different microphones.
The difficulty is really managing all that radio spectrum. So the problem is for the operator on the ground to figure out how he's going to use all of those beams and change them around if he wants to be agile with them. But the satellite is, yeah, very agile. Essentially, you have a link from the ground with telecommands. You have software on board. You can tell it what you want it to do, and it will adjust immediately. So yeah, but if you change all the beams around, you might be interfering with traffic elsewhere, and the problem is for the operator on the ground to solve that big puzzle of getting everyone talking to the right people at the right time.
Let's ask why and problem something like it. Let's give it an eye.
Not using an NVIDIA chip. That's what the supercomputer, the Isambard supercomputer uses. So the NVIDIA chip is the state of the art, basically. Terrestrially, it uses something like 4 nanometer process. So that's the size of the features that's being etched into the silicon is only 4 nanometers, not very many atoms thick. So they can get a huge amount on each chip. We're not quite at that level, but you know, we're a few generations behind. And I mean, it's not quite what you're asking, but it's useful to say that obviously NVIDIA is a big company and they make millions of these chips, and therefore they can have many generations and they can keep developing new chips, whereas we sell small numbers, tens of satellites, so hundreds or a few thousand chips, and we have to basically, that's the reason for making the satellite flexible, is the technology cost is amortized over very few actual customers and products compared to something like NVIDIA, which is, you know, really doing the state of the art computing. I'm happy to take more questions at the end, so I'll move on now. We want to actually talk about some of the technology components within our processor, just to show you what we're doing. So NVIDIA has a custom integrated circuit which they use over and over again in that Isambard supercomputer that we saw before. We have our own custom ASIC, which we paid for specifically for the satellite, which is why the reason for making sure we have multiple customers that will buy the same satellite. But just to give you an idea of what drives the technology, I have on the top right, again, it's a commercial chip, and in the center of this, I haven't actually set up pointer, but anyway, we'll go for a there is a chip in the center of here which is a Ethernet switch. So this is basically from a supercomputer, which is really a data center. So data centers, lots of memory, but the problem is really connecting all that together. So they have a huge amount of switching technology which is implemented in Ethernet switches, and they need the power station basically to drive the Ethernet switches. The leader of this technology is Broadcom in the United States, and this is a conference sort of demonstration board from a couple of years ago showing their Tomahawk 5 chip, which was the state of the art in Ethernet switches. So that actually, they don't say how much it dissipates, but you could sort of work out that it's about 950 watts. So when you said, can you get a kilowatt out in one chip? Yes, you can, apparently. You can see on this that it actually has inlets for water cooling, and there would actually be a metal plate over the whole of this, which has been taken off for the demonstration, so we can see it's not actually working, but we can see what's inside it. But essentially this is a water cooled system because there's a kilowatt in one chip. But what drives it is the technology is these kind of Ethernet switches, and there are two things that are driving it. One, the size of the chip is limited by what the semiconductor foundries can make masks the size, so it's called the reticle limit. And the other basically is how much I/O you can get around, how much interconnect you can get in and out, data you can get in and out. So you've effectively got the periphery of the chip to use for interconnect. You can have the world's most powerful chip, but if you can't get data in and out, you can't use all of the processing power in it. So Ethernet switches essentially have an awful lot of interconnect. Broadcom are the leader because they can get the maximum amount of interconnect in. So this chip has 512 high-speed digital inputs, each running 100 gigabits per second. So that works out as 51 terabits per second. Switch state of the art. I don't know whether anyone uses it yet because it's difficult with this huge power dissipation. But you can see there are 16 chips around it. What they are doing is converting the electrical signals to optical. And then those optical signals are routed out to connectors on the right-hand side, and then you have a forest of optical fibers to connect that to other racks in the system. And actually, the optical lasers are external to this. There's so much power you couldn't generate them in the chip or on board. So it's actually you're sending laser light in, and those optical chips are actually just modulating the light. So it's a bit different to the lower rate stuff that you actually have lasers on the chips or on the adjacent chips.
15.
How many of what?
All those chips on the side.
Well, we don't. This is a terrestrial example of the state of the art. I'm just going to use this to compare with us. But yeah, so in a router, high-end router, so 51 terabits is a bit more than your home internet router. There's just one. So all of that is a rack system. Basically, all of that box is just to do one chip in the middle here. So if you want to build a big data center, you have a big rack in a room full of of these things that looks like the supercomputer on the first slide. We have effectively a chip which is illustrated bottom left, and it's similar in technology to this big Ethernet switch. I've kind of drawn a picture bottom right. Now the high-speed digital interconnections, which is what drives the size of the chip, they're called SerDes, which stands for serializer, deserializer. So it doesn't matter too much about that, except that on the Ethernet switch, the whole of the periphery is filled with these interconnect logic driving this high-speed interconnect at tens or hundreds of gigabits per second. Our chip, basically, because it's our custom design for our telecom satellites, we take that away from two of the edges and we replace it with radio frequency interfaces. So we basically take in the signal from the antenna after it's been amplified at up to 30 gigahertz, and we convert that to digital, and we use two edges of the chip, if you like, to have lots of radio frequency circuitry, analog circuitry, and analog to digital conversion inside our chip. So our chip processes quite a lot less. It processes about 1 terabit per second per chip, but that's still an awful lot. And we do other functions inside. We have switching, but for example, this red box in the middle, which I've called BFN, is just a schematic indication of the kind of things we're doing. There's beamforming. So that's the bit that combines all the signals from all of these feeds, basically amplitude and phase corrections to the signals, which might be amplitude phase correction a second. So I mean, that number you can multiply up. So the number of chips we use is about 50, less than 100. It depends a bit on the actual size of the processor, because we can scale this up. It's a order of that, but they're not all doing the same thing. So we have some doing beamforming, some doing switching, some doing.
The previous slide had said the solar panels were 15 kilowatts.
Yes.
But these are consuming.
So we will see that this consumes of the order of 3 or 4 kilowatts. Most of the power for the satellite should go into the amplifiers that drive the transmit side. So what we want is just beam microwaves down to the ground. If it was 100% efficient satellite, all of the power from the solar powers would go into microwaves. The amplifiers that sitting behind this antenna are only about 50% efficient, maybe a bit better nowadays. So that's where a lot of the heat goes, and then a lot of the rest goes in our processor, doing all the computations, but turning that into heat inside the spacecraft. So that's an example of the terrestrial technology and how we compare with it. So actually, we have the same size chip. We have a chip at basically its theoretical limit, so it's got a maximum I/O. We're not going quite as fast, and we're not using all of the I/O in the same way this Ethernet switch does. I have another prop to show you. This is just a 3D printed plastic model of one of the printed circuit boards on our in our processor, and these big square blobs are the ASIC packages. So you can see they're about 5 centimeters on the side, and there are more than 2,000 connections coming out the bottom into the printed circuit board. So this is a thick, complicated printed circuit board with many layers to route all of those signals. The other thing you can see on this, while I'm at it, is that the components on the periphery are all electro-optical converters. So this is converting the electrical signal from the chips into optical, so that we can send it over a larger distance. So if I move to the next slide, the other technological challenge I've already mentioned is connecting all of these things together. These very high-speed serial electrical signals generated by SerDes don't travel very far in a printed circuit board. They just get attenuated, they disappear, they fade out. They also tend to interfere with each other and interact and generally get corrupted. So routing these signals inside a many-layer printed circuit board is a major challenge. So I've said it's more than 20 layers. I'm not going to say exactly how many. We're talking about rates of about 25 gigabits per second in our case, which is not state of the art, but it's not far off. I mean, if you want a comparison, if you think of your Ethernet connectors at home, you're typically using gigabit Ethernet. And if you're a high-end user, you might use 10 gigabit Ethernet, and we're talking about 25 gigs. So it's more than casual user type rates. But this won't go very far over a printed circuit board technology. So we have to convert it to optical, and then the connections between all the boards are actually bundles of optical fibers. So if you, I don't have a picture of it here, but if you look online at that Isambard supercomputer, we saw the front with all the water pipes. If you look at the back, it's a forest of optical cables. It doesn't look very tidy, so they don't tend to show that one so much. We basically the same architecture. So these high-speed serial connections are a technological challenge. We have to move to a high-frequency printed circuit board material. So we have radio frequency signals from the antenna up to 30 gigahertz, and we also have digitally switching signals, the switching at nearly 30 gigahertz as well. So it has to be a special printed circuit board technology. And for the space industry, that's a big deal because we have to have space qualified mounting of all the components that go on this printed circuit board. They all have to be proven to survive in a space environment, our space environment, for 15 years plus some margin to operate. So the processes may be the same, or they may be different to a different printed circuit board, but we have to prove that they're robust. So there's more than 100 different types of components that we've had to qualify mounting just because of the change of the printed circuit board for this processor, this satellite. So it's a major technical challenge. You don't really have that to the same extent if you're doing this for a terrestrial design. So it takes us a bit longer to knock out a new design. It takes us a few years, as opposed to a few months for a terrestrial chip manufacturer. So the other thing that we have to worry about in the space environment is, or not in the space environment, getting there is the launch environment. So we do all kinds of testing, but one of the most important types of tests we do is vibration testing. When this is launched, the rocket is quite a violent machine, and all of our electronics get shaken very heavily. So we test it on the ground by shaking it in a similar manner. And I've just got a couple of inset diagrams here to show you. This is a picture of what an electro-optical converter looks like. So you can see some pads on the bottom, which will be soldered onto the printed circuit board, and you can see effectively where a fiber ribbon comes out the other side. So that's effectively has laser inside the package that will convert electrical to optical one way, and a photodiode that will convert it back again the other way. But if you imagine putting this on a printed circuit board, connecting up some fibers and then vibrating it, the obvious thing that's going to happen is that the fibers are going to be, if they're not tied down properly, are going to waggle all over the place. You can see a sort of a finite element model here with this end waggling downwards and then waggling upwards. It's all going to break. So everything has to be very carefully designed for that launch environment as well as the space environment. So I just mentioned this as a technological challenge. It's similar to terrestrial, but there's a lot of things that we have to do for the space environment, which is on top of what we do on the ground. And then finally, the third area of technology that I'm going to mention is heat dissipation. So I've already said that supercomputer Isambard it heats one of the university buildings, but it's going to heat the local housing estate as well if they get round to it. Did I say 5 megawatts or 50 megawatts before? I think I think it was 5 megawatts. So yeah, that's a typo. Sorry about that. We dissipate about 4 kilowatts in our processor, and we're doing about 1,000th of the number of floating point operations. So we're similar power per floating operation. Our operations are customized rather than fully programmable. So that's how we keep up without having quite the highest technology. But to get the heat out, terrestrially, you use water cooling. So you have all these hoses, red and blue hoses, you have pumps, you have heat exchangers, all that kind of stuff. There's an awful lot of paraphernalia. That isn't a very good solution in space. If you imagine a pump, how long is that going to work for 15 years in space? If it goes wrong, if you have a leak, what's it going to do? I mean, everything's going to overheat and the leak is going to freeze on the sides of the spacecraft. It would be a horrible mess. So we can't do that. We can't use fan cooling or anything like that. There's no air. So we can't use the same techniques you might have in your desktop PC or laptop. So heat dissipation is really a big problem for us. So it's for supercomputers, it's a massive problem. But for us, it's also a massive problem for slightly different reasons. We're a smaller scale, but we have bigger difficulties. So we have a novel technology that does that. So the pictures I've got show you some of the metalwork. It's the metalwork basically in our processor, the framework, the box that takes the heat away from our chips. So what happens is that each of the chips basically the heat doesn't go through the printed circuit board. That's made of some insulating material that doesn't conduct heat. We actually have to have a mechanical structure whereby we can squash the top of the chip against a thermally conducting material, which can then be connected to the or in contact with the frame, and then the heat gets conducted away purely by conduction through the metal frame. So what we have is the metal frame. Let's give you an idea of the size of our module. It's a bit bigger than the one we saw before. So we have more than one of those printed circuit boards in here. This will be rammed full of electronic components. And then actually this corresponds to the top part of so this is just to give you an idea of the size. This corresponds to the top part of my diagram, which I've whited out, so you can't see all the electronic components because those are secrets at the moment. And then what we have here is a core. So this is basically a thermal core. It's a big lump of metal, essentially. It's got all the right shapings and stuff so that the chips, the hot parts, press down on these pads here to make good thermal contact, and then heat's conducted through the metalwork to the wall of the spacecraft or the panel of the spacecraft on which the processor is mounted, and then it's carried away to the radiating panels of the spacecraft. So spacecraft can only get rid of heat by radiation. So we have basically radiators that poke out the spacecraft that just on the shady side that get rid of all the heat, and we connect to that. So actually we do actually use liquid cooling, but we use passive form of liquid cooling in the form of heat pipes. So heat pipes increasingly used in high-end terrestrial stuff, and I've shown you a little picture here of a copper heat pipe. So basically this is a copper water heat pipe. So you've got a copper pipe. It has water inside, but at a low pressure, so there's room for it to vaporize when it's heated. And you have some sort of wicking material, which is like little pellets of copper or something stuck around the side. And the idea is that one end of that is at a hot point under a chip. The other end is at a cold point. In our case, it would be a radiator panel, but anyway, so somewhere where the heat can go to. And the hot point evaporates the water, turns to steam. The steam moves down the pipe and it condenses somewhere else where it's cold and transfers the heat. And then it trickles back via capillary action, which is what all of that this lumpy material in here is intended to help. And it goes again. So it's completely sealed and it's completely passive. It's like a refrigerator, but without a pump. And that's a heat pipe. So heat pipes are very good in space because the big downside of heat pipes on the ground is that the water won't trickle very far, and it particularly won't go uphill. So if you have it going vertically up against the gravity, it will only go a few centimeters. One of the advantages we have is we're in a zero gravity environment, so it will go more or less as far as you want. And it's quite remarkable. These things are maybe 100, they could be anything up to 1,000 times more conductive than the solid metal equivalent. Because the actual medium moves, It's a lot more conductive than even the pure copper. So actually we embed that in our metal frame. So basically we have what we call a module full of electronics. On one side, this thing full of electronics, we have a metal core with heat pipes embedded in it in the middle, and then we make a sandwich with two of these modules coming together, and all the heat going down into the middle. So at the bottom, you can see this is the edge view of the core. So you see it's quite thick. So actually, there's a lot of metal work to conduct the heat, but you can see these little grey bits here are the ends of the heat pipes that are bringing heat down from the middle of the processor, and they're bent round and then milled flat to basically improve the thermal area to conduct the heat into the spacecraft panel, which is going to take the heat through the spacecraft. And the spacecraft itself will use heat pipes to get stuff around the spacecraft structure as well. That's been done for many years. It's more unusual to actually put heat pipes inside like this processor. So that's how we call our heavy duty processor. So finally, everything that goes into space, particularly in geostationary orbit, where it's going to be up there for 15 years and forgotten about, or not forgotten about, but you certainly can't get it back and do any maintenance on it, has to be thoroughly tested. So here is a picture of our first flight processor, actually, or a segment of it, in a clean room for testing. So testing is complex. I mean, typically we'll do functional testing, which will prove everything that our processor is supposed to do in terms of functions, but also performance. Is the signal to noise good enough for the communications we want to do, for example? We will put it through environmental testing, which will include vibration and shock to represent the or ensure it survives the environment it's going to get during the launch and early operations phase when there are explosive bolts deploying solar panels and things like that. And we will also, because of the heat being such a problem, and because the real processor will operate in a vacuum, we put it in a big vacuum chamber, pump out all of the air, and switch it on, and basically check all the heat dissipation technology works. So measure the temperature everywhere on it, and prove it's working. So that's called thermal vacuum testing. So the picture I've got shows the functional testing stage. So this is not going in any environmental thing. The processor is the bit in the middle, and actually what you can see there is 3 of the sandwiches I described put together into one box. So each of those 3 layers is a thermal core with 2 modules of electronics on either side of it, 3 of them together forming a box. And on the left we have an RF test rack, which will generate lots of signals to represent the traffic that would go through and test that work. And on the right hand side, control, power, all of the other things that we need to actually power this up. And the interesting thing is that this is on its side. So we have a thermal table basically, which allows us to control the temperature at the back, a sort of thermal plate at the back, and then these things are stuck sideways. Normally they'd be on a tabletop vertically, and that's because we've got these heat pipes in the gravity environment, and we have to make sure they're all horizontal. So we have to test it on its side. Till it gets into space, it will never be tested exactly as it's used. So those are basically the technical points and the challenges that I wanted to explain of something that we're building now. So just to summarize where we are, the processor is called Hyperion. That's just our name for it. Entirely designed in Stevenage and built in Portsmouth, so it's a big UK activity. We have a very large number of new technologies and up-to-date electronic technologies going into this processor and into space for the first time, and some novel features to make that all work in the space environment. And currently we have 10 spacecraft under contract with this. We have similar number of customers, some of them order more than one, as you've already asked, so it's 10-ish, just under 10 different customers, so that part's worked quite well. And we have a similar number sort of in negotiation at the moment. So the first processor is processors coming off our production line this year, so they're delivered into the ground to be integrated with the satellite, and the first launches will be next year, and then there will be several per year for some years to come. So hopefully I've given you a little flavor of satellite we've and the technologies that we're doing, and hopefully I haven't disillusioned you too much by calling it supercomputing power. I've explained enough that the technologies are similar to state of the art around. So that's all I had to say, but I'm happy to take any questions if people are still awake. I don't know if you want to do a mic or whether we can all hear.
Fine. Separation and top levels subject to that confidential.
I just don't know them.
We have our head of vibration sitting a few bits behind, but there will be specific levels for specific satellites and specific launchers. So, for example, if you stick it on a shaky old Russian launcher, I don't actually know which is the shakiest. You'll have to do a higher level than a smooth RAeS. So, I mean, at Airbus, we basically have some sort of generic requirements for this type of equipment going on this type of geosatellite, but it will be very different for different types of satellites and different types of equipment, particularly, if it's going on a different part of the spacecraft. Processor sits inside, it's protected as it can possibly be from the outside environment. The antenna pokes out the side, for example, and it could, maybe not for vibration, but for most things, it gets the worst environment than we do in the electronics part. So yeah, I have no idea. I mean, I've seen the things vibrating on the shaker and they kind of blurred. So yeah, you don't stand very close to them because if anything flies off, it's gonna hurt.
Don't really in your best.
Yeah.
I'll now reveal myself to not be any kind of rocket scientist. Obviously, this has a huge amount of power draw and power requirements, and I'm guessing that it has to be completely uninterrupted at all times. Obviously, it's got the solar array to draw power. What sort of provisions does it have for when it's in the event it's shielded by something, or presumably in night side of the Earth? Is it mostly batteries that remain to space, or has it got?
There is quite a lot of space for that.
People here will know more about that than me, but the satellite's almost always in the sunlight because the plane of the Earth's orbit rotation is tilted. So if I went back to the first slide, if you imagine the sun was off to the left, which I guess it is because the way it's illuminated, and you imagine that the satellite's quite a long way from the Earth because it's a geostationary satellite, so it's about 6 times further away from the Earth than the radius of the Earth. It's kind of usually above or below the plane where the sun is. So it's only in eclipse seasons, just like we only have eclipses near the equinoxes, lunar eclipses near the or solar eclipses near the equinoxes. It's the same with these geos because it's very similar to the moon going around the Earth. So for those short periods, a few days a year, when it does go into the Earth's shadow, yes, you have batteries, and there is quite a lot of space on the satellite for batteries, but it's actually only a small amount of time that they're used for in operation. They're also used when you first launch it before the solar panels are deployed. So they start off charged, as far as I understand it.
But in that case, the
processor wouldn't be working. And when you're going into the eclipse, then yes, we have to support quite a high power for some number of minutes. I don't know if anyone here knows how long that is. Okay, so just over an hour. Yeah. So there's a lot of there's a lot of
Presumably obscuring.
yeah,
You'd be able to.
the moon is 1 degree basically.
from Earth, and that's about the same as the sun. So it's quite a big chunk of sky that it's covering. Well, it has to be managed by all the operators. So people on the ground with big antennas have to be very careful not to point them at the wrong satellite. Ideally, the low Earth ones, because they're moving all over the place, use different frequency bands. But typically, there are more of those, and they have some big, powerful people behind them. So there is fight for the radio spectrum resources. between the different areas. Fortunately, that's not our problem. That's our customers, the operators, and the International Telecommunications Union, which regulates and agrees all of these things. Yeah, in low Earth orbit. So all of the numbers scale a bit differently, but it's still extremely challenging to do what they want to do.
Do data in, they would do some synchronous in the data processing.
Are you talking about
The data center type thing in yeah, I don't, that's new, so I don't know anything about that. What they're claiming is that it's more efficient because it's solar powered anyway, which is a little bit strange because it costs an awful lot to launch these things, and in low Earth orbit they kind of fall back to Earth every few years anyway. So yeah, so I don't know, that's too new. You have to read the internet, or I will try to catch up. But yeah, I don't understand the logic for why they even want to do that, let alone how. But you know, there are telecommunications satellites, so for the traffic, they have very high challenges and similar to the ones I've been describing, but the numbers and the actual requirements are all somewhat scaled differently. So I've focused on the geostationary because it's easier. Yeah.
How many of these
single?
That's really just a question of, I mean, if they're using exactly the same frequency, then effectively they have to be the same operator somehow coordinating them so as to not interfere with each other. And then it's a orbital question, I guess, how many satellites can you put there and how do you manage them? If you mean different frequency bands, different services, then not many, because there aren't many different frequency bands. So as far as I know, there aren't many satellites in each possible orbital slot. I don't know the answer precisely. It'll be a small number. If you imagine that you had two satellites and one did one half the band and one did the other half the band, and you could double the amount of traffic somehow by doing that, then you could do that. But the way this is scaled, the example I gave, there wouldn't be too much benefit because we're processing the whole band in either, and we're limited more by the spectrum than we are by the processor. But for the use case I gave, so it doesn't make very much sense to do that for this stuff, right?
That's like creating redundancy, or is it adding to existing capacity, or
That's
The answer I gave before with the customers. So if you're one country, maybe a small country, you might just have one satellite serving the whole of your region, and that's the advantage of geostationary. You only need to launch one. If you want to do a low Earth orbit thing like Elon Musk, you need 1,000, hundreds or thousands, and it costs a lot more. So our one satellite goes in high orbit, needs a big launcher, is quite expensive. It's a big satellite, it's quite expensive, but you only need one. So that's really all of the customers we're talking about are these regional operators, or most of them, wanting to cover their country from satellite. There are, I mean, because it's a flexible satellite, there are also these international operators that basically have, 10 or 20 satellites, and these might be as a replacement for a satellite that's going to run out in some number of years' time, going to run out of fuel basically. So and it might be, they fly spares, not very many. Normally they launch something when fairly soon before they need it, so that it's not wasted, all of that money. So yeah, a big operator will have a number of satellites of different types flying around in different orbits and different parts of the world, serving different customers, and they have to replace them on a regular basis.
geometry? That's it.
I've deliberately avoided doing it. What I did say, I should have forgot to say it was on the slide, was
It's
but not ridiculously bigger. You can
measurement upsets an issue for the processing.
all digital electronics in space suffers from single event upsets caused by radiation. So typically it's cosmic rays, so high energy ions coming, e.g. from the center of the galaxy, black hole at the center of the galaxy, whizzes stuff around all over the place, and it's got such high energy, even though there aren't very many of them, they go through everything, so you can't avoid them in space. And if one of those hits one of our bits of silicon that's processing a naught might turn into 1, or 1 might turn into a naught, and in the digital world that could kill everything. So all of our design everywhere throughout has to be tolerant against that, so we will have
It's transient. Oh.
so there will be
some things which are less sensitive and others which are more sensitive. So yes, if you're talking about the signal and it just there's a bit of a spike in, well, that's just like noise. We don't care. If it's the thing that turns the satellite on or off, it's going to be a bit more protected, you know, and there's going to be a whole range in between with different techniques that we have to apply to protect against that kind of problem. Yes.
Sure that your silicon process years on.
We have a good plan in place for that, but again, I'm not going to say what it is. yeah, we have a secure supply of all of the chips that we need for the processing ASICs anyway. Yeah, I can't speak for all of the other 100 different components on the board.
Is it also done in Portsmouth as well?
yeah.
I mean, the chips are manufactured at Semiconductor Foundry. There aren't very many of those around the world. They're either in Taiwan or America, typically, or owned by those companies that are based there. But the manufacturing of the printed circuit boards, the population of printed circuit boards of components, the putting all those together into a board, the metalwork, all that kind of stuff, yeah, it's all put together in Portsmouth and tested in Portsmouth. Of those. There's only 2. I'm not going to say which one it is really. So if you trace them all back.
With gold dots in the back. That just because everything.
The dots were the electrical connections, so they're soldered onto the printed circuit.
Okay.
Yeah, so that's what it's all called service now technology. Machine places with components on automatically, through ovens
The solder are exactly the right amount, etc., on like a conveyor belt. So that facility is in Portsmouth. That's what we just do, manufacture it. Effectively, that's what we're doing. And then there's the manual work to assemble boards into frames and things like that afterwards, as well as testing it. So yeah, that was just effectively where the solder goes, that you could see on those components. And the same, you saw the connections.
But it was about 60 by 60.
Yeah, I just said more than 2,000. The number's not far.
But yeah, it's of that order. So I mean, if you imagine it's roughly a 5 by 5 centimeter package, and you imagine those balls are a millimeter apart, and you can see it. You know, that would be 50 by 50, 2,500. That's the sort of number, yeah. And that's basically the. I mean, you can get finer pitch packages, so you can put the balls closer together, the pads there closer together, but that's more difficult to get working reliably in space for 15 years with the daily variations in temperature expanding and contracting and trying to break everything. So we have solutions for that, but again, I can't talk about what those are. Those are very proprietary. Soon before anyone.
Just for general information, not necessarily project specific. You advanced the thing with 4 nanometers. What was that for? A feature in the silicon.
So that was the NVIDIA is the biggest semiconductor company in the
world, and they have the they are earliest to get to market with the most advanced technology. So as far as I know, that's the leading edge. And that 4 nanometer is the smallest feature size, if you like, the resolution of the mask that they can put on the silicon. So if they build a transistor, the edges will be smooth to within about 4 nanometers or 40 atoms or whatever that is.
So if you then take the size of the chip and figure out how big a transistor is, you can figure out how many billions of transistors they can fit on a chip. So I know that ours, it's difficult to say how many transistors there are on a chip because a lot of ours, for example, is memory. Memory is not made of transistors, but you know, you can easily fit a billion transistors on a chip if that's what you wanted to do. I don't know quite how many billion it really would be if you did that because we haven't done that. But that, so the feature size of our chip is going to be of the same order, but it's going to be a future generations away.
The 4 nanometers, yeah, I haven't seen anyone else doing that. I thought 7 nanometers was the leading edge. But yeah, this NVIDIA chip is 4 nanometers, so
Just demonstrate one.
Yeah, I saw.
yeah, I saw a big semiconductor factory being built in Sicily, and it was like 3-story buildings. So the first story building is just concrete pillars, big forest concrete pillars, and then they have a floor on top, and the pillars are just to kind of dampen the machine to make the silicon, and then above they have all the plant, you know, all the nitrogen and water and all those other things. And yeah, I did look, and they didn't really have a good answer for that. Yeah.
This is kilowatt dissipation after the heat is taken out, the heat sinks and what's the temperature of the chip itself?
Again, I can't tell you exactly. I mean, it's so our processor is 4 kilowatts, and that's a number of chips. So our chips are less than that. Again, I don't want to say exactly how much, but generally speaking, you don't want to go much above 100 degrees for silicon. The higher you go, the quicker it wears out. So if it's your iPhone and they want to sell you another one in 2 or 3 years, then they don't care if it goes a bit hotter. We have to keep ours cooler than typically the average because we have to make it last for 15 years. So there will be a sort of exponential law of how fast your semiconductor wears out, and we have to keep it below that. But there will be a whole distribution of temperatures from actually on the silicon die to the package to the thermal stuff. So there isn't really one temperature. You could say there's a junction temperature in the silicon, and that will be the number that they do. And I don't know what that is, so I wouldn't be able to tell you anyway. But I don't actually know what it is. But of order 100 degrees centigrade is going to be the right ballpark.
So you've got big solar panels.
Yeah, so actually on one sat, the last picture, which I just had as a decoration, shows the larger picture.
At the bottom shows the OneSat satellite stowed. That's what it looks like when it's launched in the rocket, sorry. And actually, you should be able to fit 2 of those, or maybe even 3 in a large launcher. So it's not quite flat pack, but it's aimed at that. But you can see the top panel, the top surface of this is actually a rotatable radiator, and there's one on the bottom. And you can see on the right hand side they are actually deployed. I don't know whether that's a realistic deployment or just an artist's impression. So they will be on the sort of shady side of the spacecraft, away from the sun, radiating the heat.
In the picture, they're edge on, right?
Yes. I don't know how they work, to be honest. I mean, it's just, but you can see them on all of the satellite pictures. So I know that's what they are. I don't know exactly how they work. Okay, if you're happy, we can stop there.
Thank you very much for Robert for his amazing presentation of this very interesting topic on the satellite processor. I just also would like to mention that our next upcoming event of our public series is going to be on the 8th of April about the Young Professionals Lecture Competition over at MBDA. So if you're interested, you're all welcome to come along. And again, thank you very much for the presentation, and thank you very much everyone for coming.